Okay, so last time we left off with a very, very important idea. That was that Pythagoras is good. Pythagoras is good because if you know two sides on a right triangle, it will give you the third one. But knowing the ratios is even better. Because knowing the ratios, if you know the ratios on the sides of the right triangle, all you need to know is just one side. If you know one side, the ratios will give you the other two sides. Okay, that's what we did last time. And let's just remember here, one of the crucial ideas was the 30-60 theorem that said that on a 30-60 triangle, okay, so if you have a triangle where you know the sides are, you know the angle, this angle, one of the angles is 30, the other one is 60, and the other one is a 90-degree angle, then we knew exactly at that point, we knew the ratios. That was a nice thing because we knew that across from 30 is a small one, across from 90 is the hypotenuse, and we knew the following ratio. To go that way, the ratio is 2. You multiply by 2. And across from 60, you find the medium one. To go that way, you multiply by square root of 3. That was good. It was a day of the ratios. Knowing the ratios is good. All you need is one side, and the ratios will give you the other two sides. So today, the purpose of the lesson today is to add one more type of triangle, or maybe two, to the list of triangles where we know the ratios. So here, I propose that on the 45 triangle, we also know the ratios. We know the ratios, and they go like this. On a 45 triangle, the ratios go like this. By the way, on a 45 triangle, if this is 45 degrees and this is 45 degrees, I don't always draw these to scale, but I try to do it in this case. If I draw it to scale, you see across from 45 and across from 45, which side do you think is bigger? If this angle is this big and the angle is exactly the same, if you accept the notion that big angles make big sides and little angles make little sides, then that leads you to accept that equal angles would make equal sides on a Euclidean triangle. So these sides are the same. So whatever you call this one S, then the ratio here will be equal. That side will also equal that side. And the ratio for the hypotenuse, which it would be across from 90, there would be S times the square root of 2. So to go that way from this leg to the hypotenuse, all you do is multiply by the square root of 2. That's what we call knowing the ratios, and when you know the ratios, then it's a good thing because all you need is one side. From one side, the ratios will tell you all the other ones. So a couple things are necessary now to finish explaining this. First thing is we need to practice exactly how we do this. From one side, we figure out the other sides. Second, why? Why is it the case that the ratios are the hypotenuse is the square root of 2 times the small one? So we need to practice how to use it, and we need to explain why. Let's practice how to use it first. So suppose someone gives you a 45 triangle. So there it is. This is a 45. Suppose that's given as promised. On a 45 triangle, all you need is one side. From one side alone, you should be able to figure out the other ones. So suppose they tell you this side is 3. That's it. That's all you need. And from there, you should be able to figure out the rest. Because you know that the two sides are equal. And so if this is 3, that one has to be 3. And you know that to get from there to the hypotenuse, all you do is multiply by the square root of 2. So this would be 3 times the square root of 2. See how easy that is? Super easy, right? Let's backtrack a second. Well, let's leave that there. What we want to do is point out that the sides could be anything. Let's delete this. Delete that. Delete that. Now, suppose that again, all you really need to know is that these sides are equal, and that to get from either one of the legs to the hypotenuse, all you do is multiply by the square root of 2. Okay, so If this side was 5, what would this one be? Well, that one would have to be 5. And what would that one be? Of course, it would be 5 times the square root of 2. It's that easy. You say, well, that's easy when that one is given. What if this one was given? Suppose that one is 7. Well, again, these two are equal, so that would be 7. And to get to there, you would just multiply by the square root of 2. See that? Say, okay, what if the other one was given? What if this one was given to be 7? Well, to go this way, you multiply by the square root of 2. That means that, let's erase this. That means that to go this way, to go that way, you would have to divide by the square root of 2. So this would be 7 divided by the square root of 2. Now these two are equal, so this would be 7 divided by the square root of 2. Get it? Too easy, right? You know, you could. What if this one was? Well, again, we have to erase this piece. What if this one was? Say the hypotenuse is given. Again, you got to know that to go from the hypotenuse to the small one, you would divide by the square root of 2. So this is 12.7. Well, this would be 12.7 divided by the square root of 2, and these two would be equal. So this would also be 12.7 divided by the square root of 2. I told you. This is the same lesson as before. If we know the ratios, all we need is one side. If one side is known, the ratios will give you the other two sides. And it just so happens for the 45-45 triangles, we also know the ratios. The ratios are, as stated here, I could put it right here. The ratios are the hypotenuse is equal to the side times the square root of 2. And the other two sides are equal. Okay? Sides are equal. There's sides that are not the hypotenuse. Oh, this is too easy. One thing left to explain is why. You should own everything that we explain here. Exactly. You know, don't just take my word for it. Try to understand. Try to seek a convincing argument. Why or why couldn't it be that way? So the argument would be similar to the last one. If you have a right triangle that's 45, 45, why is it that, well, we already explained about why these two sides are the same, because their angles are the same, and if you accept the notion that big angles make big sides and little angles make little sides, then you have to accept the notion that equal angles would make equal sides. So these two have to be equal. And that's the hypotenuse. Well, from there we can use Pythagoras, right? Pythagoras would say that h squared is equal to s squared plus s squared. And that would tell you that h squared would be 2 of these. An s squared plus another s squared gives you a total of 2 s squares. And, oh wait, there's more. H would be equal to plus or minus the square root of 2 s squares. And if you accept the notion that the hypotenuse is a positive length, then that would have to be 2 times s times the square root of 2. Again, assuming that s is positive. Okay, that's a proof. That's why the hypotenuse is the square root of 2 times the small one, and it gives you this ratio. The ratio is these two sides are equal, and to go that way, you multiply by the square root of 2. Of course, to come back, you divide by the square root of 2. Divide by the square root of 2. Okay? It's a 45-45 theorem. Easy, huh? Okay. Alright, so let's take another case. For some of you, this one's just for fun. For others of you, it will be a crucial part of the rest of the trig course. So these triangles here. What if I told you that one of the sides is incredibly close to 0? Would that still be a triangle? Well, it depends on who defines it. Really, there's no police authority out there who ensures that everybody uses words in the same way. We all use language to communicate, and the words can be defined any way you want. We sort of try to keep them standard just so we know what we're talking about. But this question comes up. For example, if I drew this, would that be a triangle? And some of you may say, no, it's just a line. But others of you might get a little bit more creative and say, well, maybe it is a triangle. You got the two sides here right on top of each other, and you got a side here that's size 0. So maybe in that sense it is. In fact, to make sense of our trig functions later on, we will consider this to be a triangle. In fact, it's such a special triangle, we'll give it its name, and we'll call it almost triangle. Almost triangle. And to draw it here, it's hard to see the triangle, so we'll often try to draw them with a side that's approximately 0, so that we can make sense of the three sides, and maybe we can even label them. The point also here is that on the almost triangles, we know the ratios. This guy's always 0, and these two sides are always equal to each other, or approximately equal. So if this is 5, for example, that would be approximately 5, and that would be approximately 0, and this angle is approximately 0 degrees. Okay, that's the way we'll handle these almost triangles. So a lot of times, for example, maybe the triangle is this way. You say, whoa, that doesn't even look like a triangle. And if you can just imagine the two sides here and the opposite side being 0, then that's okay. But if you need a little inspiration to imagine that, you may want to draw it this way, just approximately 0, approximately 0. And in that case, as long as you know one of these two sides, you know the ratios, these two are equal. So if this is 7, for example, these two sides have to be equal. This will be approximately 7. This angle right here will be approximately 0. And that's how we'll handle these so-called almost triangles. Okay, they could be facing any way you want it. For example, sometimes you see it that way and say, whoa, that doesn't look like a triangle. And you'll need to remember that, well, maybe it's an almost triangle. If we could just draw it off of the side here, approximately 0. This angle right here is approximately 0 degrees. These don't go like that. They're more like this. If this is, I don't know, 8, for example, this would be approximately 8 too. In size. These two are approximately the same size. So there you go, almost triangles, for fun for some of you, and for a crucial part of the trig functions for others of you. Okay, alright, I think I'll stop there, and we'll see you here next time. Peace.